Everybody, welcome to Introduction to Astronomy for May 2022. My name is Chris Benton, and tonight we're talking about measuring distances in space. Last month, I showed you this absolutely gorgeous, stunning picture of this lovely spiral galaxy, NGC 4526, and it was quoted at being 55 million light years away. We asked the question, how do they measure such distances in space? And we proceeded and we had a good discussion and we answered that question with various principles and methods. We talked about the concept of light years, a light year being the distance that light travels in a year, which is 10 million kilometres. We introduced the concept of a parsec, which is 3.26 light years. And then we discussed various principles and methods that astronomers use to measure these sort of distances. This month, we ask another question. How do they know their measurements are accurate? How do they know that they are precise enough? Let's find out. Because that's why tonight's talk is titled Measuring Distances in Space, Part 2. The cosmic distance ladder and the Hubble tension. And tonight you're going to learn all about the cosmic distance ladder and how it's the tool that astronomers use to measure the distances to the stars and the galaxies as accurately and precisely as possible. We're also going to talk about the Hubble tension, and you'll learn how astronomers try to measure the current expansion rate of the universe by two ways. One is measuring distances to galaxies in what we call the local universe, how the universe appears to us in its sort of latter years, if you will. And secondly, by taking measurements in the sky of how the universe appeared to have looked in its early years. But importantly, that is going to reveal a serious problem with astronomers' ability to measure distances through space. So I've split the talk into sort of four main chapters. Firstly, we're going to have a brief revision of the relevant principles and methods that I covered in part one, but just the relevant ones to tonight's discussion. With just some brief extra few little sort of emphasis on a few points relevant to tonight. Then I'll talk about the cosmic distance ladder, how the astronomers use it to calibrate these methods. And then we're going to talk about that Hubble tension that I've just introduced you to. And then, we'll talk about we'll go with some three messages for you to take home, sticky messages. Now, I have handouts for both part one last month and a handout for tonight. If you'd like copies of those handouts, just feel free to send me an email on membership@astronomy.org.nz. It's written down in the slide. Just say, hi, Chris, just watched your talk. That was great. Could you send us a copy of the PDF, of the handouts? And that's cool. Equally, if you didn't see part one and you want to go back and watch it, you should be able to do it just from this YouTube channel, but I appreciate sometimes you go to the YouTube channel and there's a lot of different videos there and you have trouble scrambling around for last month's. And if that's the case, feel free just to send me an email and I can send you the link directly to part one. So let's move along. So with the relevant principles and methods, last month we picked those five main methods, geometric, trigonometry, right through to standard rulers. I'm going to focus on those top three tonight: geometric, trigonometry, standard candles, and spectral redshifts, because those are the commonly used ones and they're the most relevant to tonight's talk, the angle I want to put on tonight's talk. So let's talk about geometric trigonometry and how they measure distances in space with that. Three main ways: laser and radar, parallax, and water megamasers. So the lasers and radar, which very briefly, astronomers are able to fire laser beams up to reflectors on the surface of the moon that the Apollo astronauts left behind there for them, and they measure the time that it takes for the light to go to the moon and come back again. And of course, they know the speed of light pretty accurately. It's pretty easy from then on to work out the distance by just the time it took. And similarly, they do it by transmitting microwaves to the surfaces of planets in the solar system and measure the time that it takes to go there and come back again and work out the distance. So that's really good for doing measurements within the solar system, but not much beyond there. So we now move ahead to review stellar parallax. And parallax, if you recall, essentially is measuring the apparent movement of an object that you're interested in, and when you view it from different positions, seeing how it moves, apparent movement in relation to things in the distance. And we talked about a good way is using your finger as a perfect way of doing that. Hold your finger up to your nose, close one eye, see where it matches up at some distant point in the room, and then swap eyes and notice how it's moved. Move your finger out and do the same again, one eye, and you'll notice once again the finger moves, but less so the further you push it out. And so that's the general principle, that the apparent motion of an object when you're looking at it in relation to things in the distance moves when you look at it from a different angle, and the further away you look at it, looking at an object, the smaller that amount of apparent motion. So astronomers can do it from the ground on Earth, and they usually pick 2 periods 6 months ahead. I've got here in June. For example, they observe their target star here, a nearby star, and they make a note of the sort of fixed background stars here. 6 months later, they do exactly the same, say in December. They take an image of the star they're interested in, and in particular make a note of the background stars. They draw this type of diagram up and they make note of this angle here called the parallax angle. And they use a formula which we discussed, d meaning the distance, and the distance is in parsecs, and a parsec, remember, is 3.26 light years. So the distance in parsecs equals 1 divided by the parallax angle of the star, that's this angle here, in arc seconds. And you'll recall an arc second is a 60th of a degree across the sky. So it's 360th of a degree in the angle in the sky. Now, so as we did with our little demonstration with the finger, you've seen the principle. The further away an object, in this case in astronomy, the star, the smaller the angle to measure. And you can only measure an angle accurately down to a certain size. So it follows that parallax is best suited for nearby stars within sort of our local region of our Milky Way galaxy. Earthbound measurements, reliable up to about 300 light years. Of course, if you can get above the atmosphere with a telescope or a satellite, of course, you're away from all the turbulence of the atmosphere, so it enables you to get more precise measurements. And the Hubble Space Telescope with the Wide Field Camera 3 can measure with reasonable accuracy distant objects or stars up to about 10,000 light years away. The Gaia satellite, which is dedicated to this sole purpose, is to measure angles and work out the distance and positions of objects, can actually measure something with reasonable accuracy out to about 20,000 light years. Now, that's quite some distance, and considering a light year is 10 million kilometres. So this procedure is very, very handy tool to use for stars and objects sort of in our region of the Milky Way galaxy. Then we talked about water megamasers, and without going into too much detail, get that from last month's talk. But needless to say, I mentioned that most decent-sized galaxies have a supermassive black hole, millions of times the mass of our sun, at their centre. And if they're active and there's a lot of material around them, that material will form what they call an accretion disk. When material goes round and round, that's a highly energetic, pretty violent sort of place with high energies. And often within one of these accretion disks, you'll get large areas or patches high in concentration of water molecules. And you get sort of, whether it be high energy events like shock waves or X-rays going through, and they stimulate those regions, to emit really intense high energy microwave emissions, and they're known as masers. Now, what astronomers can do, they take a number of observations as things go round and round, a number of observations, and they make a note of the positions, and hence what they call the angular velocity, how these patches and regions emitting masers are moving around in the accretion disk. They then compare that with computer models of the angles that should be going on if you're right up there next to the accretion disk, and they compare the two, and they use their trigonometry to work out with computers, work out the distance to that. So that's actually a very powerful, you might sound that sounds a bit vague, but it's actually a very accurate and powerful method. It's useful for galaxies up to 200 megaparsecs. Mega, that big capital M there, means million, so 200 million parsecs. So that's, what's roughly 600 million light years away. This particular galaxy, NGC 4258, this is going to come up a couple more times in this talk. It's a well-studied galaxy. They've studied it very, very well, and they've got good, accurate measurements to it now, and so they're pretty confident in this, and that's a distance of 7.3 megaparsecs. So let's move on with our review. Let's move on to standard candles. And you recall that the principle of using standard candles, the term standard candles refers to objects that you know their brightness. You already know what they call the absolute brightness or absolute luminosity, how bright they really, really are compared with the apparent brightness, which means how bright they appear to us looking through our telescopes at some distance from them. Two of by far the commonest standard candles used to measure distances in space by astronomers is Cepheid Variable Stars and Type 1a supernova, which we're going to talk quite a bit on right now. Okay, so yeah, using these candles, comparing the true brightness with the observed brightness that we see, and we use what they call the inverse square law, or 1 over r square. R referring to the distance here. You could put a d in there quite happily. They sometimes put an r. So the point being is, if you get a source of light here of known brightness, and it goes out a distance of r with a set brightness seen from distance r, if that light is allowed to travel out to twice the distance at 2r, the light has to spread itself out over 4 times the area, which means it's going to be 4 times as dim. If you're sort of 3 times that distance away, the light, by the time it gets to you, has actually had to spread itself out over 9 times the area, which means it's going to be 9 times as dim. So you can see where the distance comes in, the figure 4 from 1 over 2 to the power of 2, and the figure 9 comes off 1 over 3 to the power of 2. So they call it the inverse square law, and a lot of things in astronomy uses that to measure how things sort of get dimmer, or weaker and weaker signals as you go out in distance. So last month we used 6 standard candles examples. Tonight we're going to focus just on these 4. So let's move along and do that. So yeah, so Cepheid variables, and just briefly, they're a type of red supergiant stars in the sky that pulsate regularly at regular intervals. There's loads of different red supergiants, different types of red supergiants, but these are a specific type of red supergiant stars that pulsate at regular intervals. And their rate of pulsation is directly related to actually how bright they are. And if you want to know a little bit more depth, we went into quite a bit of depth into why that is so last month. So feel free just to look that up. But you've got this nice little diagram here. Luminosity, meaning how bright it is. Luminosity is a function of the sun. So that means it's a factor of how bright it is compared with our sun. So 10 to the 2 means it's 100 times brighter than our sun, 1,000 times brighter than the sun for 10 to the 3. And so on. And there's different types. There's 2 different types of Cepheid variables. We talked about that last month. We'll move on. So it's the classical Cepheid variables we're interested in tonight. And here they are here. And if you can measure, for argument's sake, you say, look, it's pulsating every 10 days. You go up onto these well-published charts and you go across here, and the brightness should be exactly between 10 to the 3, sort of 10 to the 3.5 luminosities of the sun. So observing that pulsation period, you can work out exactly how bright it is. So, like everything, there's pluses and minuses of everything in life. The big advantage of using these classical Cepheid variable stars as your standard candle is they are extremely bright. As you saw in that last chart, they can get up to 100,000 times as bright as the sun. Imagine that. That's crazy. You think the sun's bright in the sky? Imagine a big star up there 100,000 times as bright as the sun. So they are quite useful. Anything from between 1 kiloparsec, so 1,000 kiloparsecs, up to about 50 mega or million parsecs. So they go out to quite some distance. You can see them with the Hubble Space Telescope. So that's a big, big plus. They're good. How about your disadvantages? Big one, multiple observations are required. You can't take 1 or 2 observations and decide, oh, how often something is pulsating. You've got to take multiple observations so you see its peak, you see it come down, and you see a pattern forming to make sure, yes, it's a Cepheid variable, it's pulsating at a regular period, and this is what its period is. What's the problem with that? Every time you do an observation and take measurements, you're opening yourself up for errors, observational errors. So that's a disadvantage. The other thing is these big supergiants, their progenitor or original stars are O and B spectral class stars. And those stars, take my word for it, are very, very rare out there, which makes that these supergiants, these classical Cepheid variable stars, are very rare. That they're not scattered all over the place. They're not ubiquitous. You got to hunt them down. As I mentioned here, and alluded to just on this graph here, there are 2 different types of Cepheid variables, which we went into a bit of depth last month. And if you've got the wrong type, if you've got a type 2 and you think it's a type 1, you're in trouble. Your data is going to be skewed. Everything's going to seem a little bit dimmer. So you're going to get things wrong. So you have to be certain you've got a type 1 or a classical Cepheid. The other thing is that measurements to classical Cepheids are best done in visual or optical wavelength range. For the light's wavelength range, it starts off at radio and microwave, infrared, optical, ultraviolet, X-ray and gamma, and it is the optical wavelength range that they are observed in. And optical wavelength light is susceptible to what we call extinction when it meets dust in the interstellar medium. So as the light from one of these classical Cepheids is traveling towards us, if there's dust, interstellar dust in there between us and the star, that dust dims the light down because the dust absorbs some of the light, so it appears dimmer, and that's going to throw your data out, and you think it's going to be further away than it really is. But also it reddens it. What happens is the dust tends to scatter the shorter wavelengths, like your blue light, and lets your red go through, much like you see with the sunset. So your light gets dimmed and it gets reddened, and that's going to upset your data. So that's another potential disadvantage of using these classical Cepheid variables for your standard candles. So we also talked about detached eclipsing binaries, and that was referring to binary star systems is when you get 2 stars going around one another like that. Eclipsing means is that the line of sight that we're looking at them from Earth is such that we see them one going in front of the other, going in front of the other. They eclipse or block each other out like that. And you can see that that's what's going on here. From our line of sight, they take turns at going in front and behind one another. We use the term detached to infer that there's no transfer of mass going on between them. They're stable sizes. Sometimes you get a big red giant or a supergiant as part of a binary system, and often you'll get mass from that transferring onto the other star, and that's going to throw all your figures out. So you want detached eclipsing binaries, and yes, they are out there. They're able to study them, but these are called a light curve. You see the light dipping when the smaller one goes in front of the larger one and so on. So that's called a light curve, and you see dips in the light. They're able to look at that, and they're able to get an idea of the size of the stars. They do spectroscopic examination of the stars. They can get an idea of their temperatures, their radial velocities, how quickly they're going around, and so on. And from there, astronomers can quite happily, with their formulas, work out the absolute luminosity or brightness of those stars. And a little comment here, the distances to these detached eclipsing binaries is usually pretty accurate, within about 1%, to all our galaxies within the local group. The local group is our local little cluster of galaxies. And it's about 10 million light years across. So we're a little bit off to one side. So if we're looking across the wider side, be talking, say, 6 million light years. So that's the sort of range, which, 1%, within 1% accuracy, that's pretty good. Now, here's an interesting one. So keep this one in mind for later on in the talk. The tip of the red giant branch. Now, this is not observing just one object or anything like that. It involves looking at a whole population of stars within a galaxy, or sometimes a cluster, and you do what they call a color magnitude diagram, also known as a CMD. And it's where you get a whole series of stars and you plot how bright they are, their luminosity or brightness here, against their temperature. And you run a whole stack of stars in there. And you're probably familiar with this sort of crude drawing here. That's your main sequence where all the stars spend 90% of their time burning hydrogen into helium. And as I've done up here, main sequence stars eventually run out of hydrogen. So two things happen. One is their core fills up with inert helium, that it's not hot enough yet to burn that helium, so it just starts collapsing and the pressure rises and rises. And the second thing that happens, you start getting a shell of hydrogen burning around the core. And that latter effect, the shell of hydrogen burning, causes the star to swell up and sort of glow a sort of a red sort of color because it increases in size, so it becomes brighter and brighter, but it becomes redder and redder. And it goes up this track here called the red giant branch on the Hirschsprung-Russell diagram. If you're interested more in this, we went into a lot of detail last month. And my point being is that they climb up here, and stars up to about 1.8 solar masses, they get what they call a degenerative core, and the pressure continues to rise, and they get to a critical temperature of about 100 million degrees Kelvin, and suddenly you get a flash of helium fusion in a runaway fashion, and they call it a helium flash, where just poof, the whole core lights up. You don't see a big flash from the outside of the star, but what you do see is when you plot all these multiple stars up here, you see the brightest stars on the red giant branch get up to a certain point and then they drop away as after the helium flash. And they call that the tip of the red giant branch. And that is the astrophysical processes going on there is well understood and it's well standardized. So that's a very good, and the other thing is it's in infrared that they do it. So that's the tip of the red giant branch. They measure a population of stars, their temperatures and luminosities. The disadvantage is it's not as bright as your classical Cepheids. It's useful out to about 20 megaparsecs as opposed to 50 for your classical Cepheids, but still, hey, 20 million parsecs, that's sort of, 60 to 70 million light years. That's still some distance. So they are very, very useful. The advantages, as I've already sort of commented on here, the astrophysics is well standardized. So you really know what's going on in there. You only need one single observation, just doing this color magnitude diagram, one snapshot of the galaxy you're looking at, and you go through all the stars and you plot them on this graph. You don't have to take a series of observations over time, which you're not opening yourself up to more observational errors. So that's a big plus. As I also mentioned, that tip of the red giant branch is highly visible in the near infrared wavelengths, they use what they call an I band. And infrared wavelengths aren't bothered by interstellar dust. They just go straight through it, so you don't get that dimming and reddening effect known as extinction that you get with the optical light wavelengths when you're observing these classical Cepheids. So you can see there's a lot of advantages of getting far more accurate with the tip of the red giant branch. Let's move on. And you're probably thinking, I didn't mention this in the list of commonly used methods. Exactly. It's sort of it's been around for a while, but it's just starting to gain some traction. The other one, type 1a supernova, and these are very large, bright explosions in the sky, and it's where you get a binary system One of the stars is a white dwarf, a nice little compact stellar corpse. The other one is a large red giant, a red supergiant, and you get mass from the red giant accretes into a disk and then it goes round and eventually gets dumped onto the surface of the white dwarf. Your white dwarf's in here, here's your accretion disk, and here's your big red giant, a red supergiant. Material gets transferred across and gets dumped onto the surface of the white dwarf. Now, white dwarf is pretty happy soul. He's pretty stable and pretty happy up to about 1.4 solar masses. A solar mass being the mass of our sun, which is about sort of 1.99 times 10 to the 30 kilograms. So that's a sort of a standard unit in astronomy called 1 solar mass. So once it gets up to a point of about 1.4 solar masses, it becomes unstable and it explodes in a massive thermonuclear explosion. Once again, because it's at a set mass, you're dealing with set figures, reliable figures, well understood figures, and it's a known brightness. All supernova type 1As, we've got a whole talk on supernova. You might think, well, how do you know it's a type 1A and not a type 2, and so on, A, B, C. You know that. We'll go over that in another talk. We've done that in the past. It's a whole topic. But yeah, trust me, you know, they know when it's a type 1A. Another brightest forms of supernova. This is the picture from the original galaxy we put at the front of the talk. This is galaxy NGC 4526, the nice beautiful spiral galaxy. And this bright light here that I didn't point out, I'm purposely never mentioned that earlier on, that is a type 1A supernova explosion going off in that galaxy. And look at, it's so bright, it's outshining its host galaxy. These things are really, really bright. And that's 55 million light years away, that galaxy. And look how bright the type 1A supernova is. They are 500, they're useful, whereby they can get seen accurately 500 times the distance of these classical Cepheid variables. So we thought the Cepheids you could see out, at 50 million parsecs. These babies, you can see them at 500 times that distance. Pretty amazing. So we've covered trigonometry, standard candles. We're just going to review briefly now spectral redshifts. And the bottom line is here is that when galaxies emit light, the light starts traveling to us. And as the light leaves the galaxy, light gets absorbed by all the little elements and atoms and so on around the galaxy. And it shows up as these, what they call spectral sort of absorption lines in the spectrum. And in the laboratory, or when you're right up against the galaxy, we know exactly where those signature spectral lines sit in terms of what wavelengths. But as the light leaves the galaxy, it's got a lot of distance to travel to us. And in the time that it's been traveling to us, the universe has been busy expanding. So those photons of light, including the absorption emission, they also get stretched out and pushed over towards longer wavelengths, or what are called the redder end of the spectrum. And it's called redshifts. So, and it's the degree of spectral redshift of these absorption spectral lines here correlates directly with the recessional velocity, or the velocity at which these galaxies are traveling away from us because of the expansion of space. It's known as cosmological spectral redshift. This is the simple formula here. This figure here refers to the wavelength at which you're looking at a certain absorption line. This is the wavelength at which you'd normally see it in the laboratory, or if you're close up to that galaxy. V is the recessional velocity. C is the velocity of light. So you know the velocity of light. We know that one. You measure this wavelength here. You know the wavelength what you should be seeing an absorption line at. So it's very easy to work out what the recessional velocity, in other words, how fast that galaxy is traveling away from us. And we showed you this Hubble's law diagram, a very famous diagram, and it shows this beautiful relationship that Edward Hubble discovered in the early 1930s, was that if you plot distance and parsecs along here on the x-axis, on the y-axis through measuring spectral redshift observations, you measure the receding velocity, you get a nice little beautiful straight line. And that's called the Hubble constant, and that represents the rate at which the universe is expanding. And this is using, of course, supernova explosions, those type 1A, to get these faraway distances to these faraway galaxies. So that's called Hubble's law. And that's how you often work out distances and velocities. You can compare them. But very importantly, it's this formula here. The recessional velocity is Hubble's constant times the distance in parsecs. Let's move on. So yeah, this is just a summary of just recapping on some of these main points with extra little bits and pieces I threw in there. You've got your trigonometry. With your, in particular, we talked about parallax and water mazes, your standard candles measuring the observed with the absolute brightness, in particular Cepheid Variable Stars and type supernova 1a are the most commonly one used. And then we just talked about redshifts, the spectral lines shifting as the universe is expanded while the light's been traveling to us. And I now want to introduce these three really important principles. No single method, all those methods we've mentioned, none of those methods covers the complete range of distances. They've all got their sweet spots whereby they're most accurate at. For example, the parallax, you saw that only got to a certain distance and the angles got too narrow and so on. So that's important. All of them are open to observational errors. When you start observing and making measurements of anything in nature, there's going to be errors involved. You don't know for certain. The other thing is the errors, the risk of errors increases with distance. And it makes sense. If you measure something sort of yay big, you're going to have some error in there, but you know the error is going to be pretty small. You start measuring something up to really, really big distances, the bigger the error is going to be. So that's an important. So those three things are important to keep in mind. And that leads us on to now the cosmic distance ladder, a tool that astronomers use to calibrate the above mentioned methods. So yeah, so let's do it. The reason they calibrate their standard candle methods is to optimize the accuracy or the precision. And hey, what is a ladder? Why the analogy with a ladder? Well, you know what a ladder is for. A ladder is when you look at something, you think, I can't get that far up. You're trying to climb up or go up a height or a distance that usually is unattainable for you. So you get your ladder out, and a ladder has nice safe steps or rungs that you can slowly, one by one, start moving up in a nice, methodical, safe manner and reach those distances in a safe manner. And that pretty much is what the cosmic distance ladder is all about, and hence the analogy. So prepared this little diagram, altered and got this diagram together to show you the principle, and it really involves a succession of all these different methods overlapping at increasing distances, and I'll show you here. So we really dealt with these three here in that last talk, so in this sort of review of the talk. So let's talk about this. So the parallax, if you recall, was pretty accurate within distances within our Milky Way, sort of stars reasonably nearby within the Milky Way. The Cepheid variables covered a lot of stars in the Milky Way, and that went way out, sort of beyond nearby galaxies, out to sort of distances where you get more distant galaxies. And then we talked about the type 1a supernova, that goes way huge, use what are called cosmological distances. And I've put the distances here. Here's your parsecs, sort of 1 through to 100. Remember parsec, 3.26 light years. Here's the kiloparsec range, the thousands of parsecs. The megaparsec range, in other words, parsecs and multiples of 1 millions, and giga referring to billions and factors of billions of parsecs. They call these cosmological distances. They're way out there. So a simple way, if you wanted to measure out to these distances, you might say, get yourself some Cepheid variable. That's your standard candle. It's pretty good. But you want to calibrate that. You want to match it up with something reliable so you know your distances are reasonably accurate. So what you do is, say you found yourself some Cepheid variables here in the sort of distant part of the Milky Way, and you pick them in particular. You know that these Cepheid variables have been examined in the past very accurately by the parallax method, which is really neat. In science, it's nice to calibrate and double check something you've done that involves a different method. And the parallax, remember, was a geometric method. Different method. Remember the Gaia satellite up there in space, launched 2013. That's accurate out to 20,000 light years. Very, very precise measurements. So you get yourself a Cepheid variable that you also know there's good data from Gaia satellite on it. So you're able to match that up. And if it's a perfect match, that's great. But if it's not a perfect match, you know to calibrate those Cepheid variable values such that they match up with the parallax values. What you do then, knowing that you've just calibrated your ability to measure Cepheid variables with the instruments and the filters and that you've got, you then might move out to some nearby galaxies. You move beyond the Milky Way to some other galaxies sort of reasonably nearby to us. And you spot a SUP1 type A supernova going off in that nearby galaxy. So you record its brightness for your standard candle purposes, and you also know you've got some Cepheid variables in that galaxy. So you measure those Cepheid variables up, and you, once again, you calibrate. Knowing that these here are now calibrated, you can now calibrate your type 1a supernova and get these figures to match these figures for distance. And then you've got this whole line here all calibrated and away you go. Now that's of course a very simplistic way of looking at it, and I did it on purpose to explain the principle, how you go different methods, preferably using a different method, which you do, geometric, to check your standard candles, and you use a succession of overlapping methods of increasing distances to work your way out. In each rung up the ladder, you're getting there securely. So you go up a little bit for further distance, calibrate, make sure you're safe there, you're happy there, you move out to another distance, calibrate again with something else that you know, and keep moving out. So that's the principle behind the cosmic distance ladder. Now, I want to introduce now a case study using the cosmic distance ladder I mentioned before how astronomers measure distances to galaxies to determine the current expansion rate of the universe. And once again, here's this graph again, recessional velocity on the y-axis using the redshifts, and they use supernova measurements here to work out the distance. They draw the line here and try and work out what this Hubble constant is, or the expansion. They call this late time measurements because we're measuring distances around the sort of what we call the local universe, or sort of how the universe appears to us in sort of more recent or latter times. So here's a study I've got that was published in 2019. It's from Reiss and his colleagues. And naturally, you know, when you're dealing with these big distances, looking at the expansion of the universe, you're having to use type 1a supernova. They're the brightest objects, standard candles, to get out there. But they calibrated them with Cepheids. And the Cepheids were initially calibrated with a combination of objects. In my simple little diagram before, this one back here, we calibrated our type 1a supernova with Cepheid variables, and then we calibrated that just with the parallax method, just one method, because it was just trying to keep things simple to explain a principle. Okay, but these guys are serious, they're professionals. So they use a combination of objects of varying distance really to calibrate the best they can these Cepheid variables before they move on and calibrate their type 1a supernova. So they get their Cepheid variables in the Milky Way and they match it up with the parallax measurements, just as we did in our simple diagram. They then move out to the Large Magellanic Cloud. The Large Magellanic Cloud is a satellite galaxy of the Milky Way. It's about roughly about 160,000 light years away from us. And they found themselves there some detached eclipsing binaries, and they used those, the measurements from those, to further calibrate the Cepheid variables. They then went out to a galaxy NGC 4258. Remember, I warned you that was going to come up again, and it will come up again later on, whether that water megamaser was going on. And I mentioned to you that's very powerful, it's been well studied, and they were able to calibrate the Cepheid variables against that for further calibration. And then they moved out to the distant galaxies and used those well-calibrated Cepheids to calibrate their type 1a supernova, which they then able to plot their graph. Now you might say, well, what was their result? Their result came back as the Hubble constant, they said, was 74.03. There's some error in there, and we'll talk about that later, but 74.03 kilometres per second per megaparsec. In other words, for every megaparsec, which is 3.26 million light years, the space is expanding 74.03 kilometres per second. So that's how they quote the Hubble constant. As I mentioned, that's a late time measurement. So remember that, roughly 74. So that leads us now to hold that thought. We're going to move on to this Hubble tension business. So that was late time measurements. Now, as I alluded to at the beginning of the talk, there is such thing as early time measurements of Hubble constant. And once again, to check anything, isn't it neat to be able to measure something in two completely independent ways to see if you're right or not? So early time and measurement involve measurements of how the universe appeared in its early years. In particular, I'm going to introduce you very briefly. It's a talk on its own called the cosmic microwave background. So let me explain a little bit first. In the first 380,000 years of the universe, it was just a hot, highly ionized plasma or hot opaque soup of charged particles. The electrons and the negative electrons and the positive protons would have loved to have joined together and come up to form neutral hydrogen atoms, but it was too hot. They were just charging around. It was just hot electrons and protons and charged particles, and amongst that two photons. Photons interact with charged particles. So you've got these photons of light radiation that just constantly whamming into a proton, interacting, spat out again, ramming into an electron. So the whole universe was a hot, seething, opaque soup of charged particles and radiation. You wouldn't want to have been there, trust me. Take my word on that. It wasn't a pleasant place. Slowly the universe expanded over that 380,000 years, whereby the temperatures dropped and those electrons and positive protons were able to join up into neutral hydrogen atoms. And suddenly those photons of light were then free to travel unimpeded through the universe. And we still to this day, we are bathing in them. What's happened is the universe, since then, over the last 13.8 billion years, the universe has, of course, continued to expand. And as the photons have traveled through the universe and the universe has expanded, those photons have been stretched out as well. And they are now surrounding us in microwave wavelengths. We are bathing in them. They permeate all of the universe. They're very low energy, about equivalent to about 2.7 Kelvin. That's why we don't feel them. They are there. And it's called the cosmic microwave background. And they can measure that. And I'll show you. Look at this. So as you can imagine, microwaves aren't the easiest to measure from the ground because they get absorbed to the atmosphere. So you send up space satellites. And there's been 3 dedicated space telescopes over time to have a look at the cosmic microwave background. There's the COBE, the WMAP, and more recently, the Planck Satellite. So let's use the data from the Planck Satellite. It's the most precise, it's the most recent one. And they were able to map it. And you see this speckly, spotty look appearance. And what all those specks refer to as little tiny fluctuations in temperature, which in turn reflect tiny little fluctuations and changes and variations in density of matter in the universe when it was 380,000 years old. So what you're looking at is the very, very first photons that were free to travel through the universe when it was only 380,000 years old. There's a wealth of information in there, a wealth, huge amounts. People often call that the afterglow of the Big Bang because the first light you can see of it. Pretty cool. So what sort of information can they get? Well, obviously they can look at it and they can tell you the distribution of matter at that time in the universe. But also they then study each of these little specks. They're able to pinpoint down the angular size it is, measure the size of it in the sky, known as the angular size in the sky, and also measure how strong or how weak those little temperature fluctuations are. And from there, they can tell you the relative proportions of dark matter, dark energy, normal matter, and so on. A lot of properties of the universe, including even its geometry. I'll show you briefly. That's a whole chat in its own right, so I don't want to get bogged down with it. But needless to say, what they've managed to do, they plotted here, this is angular size, so that how roughly each little speck looked in the sky according to its angular size is 1 degree here, 0.2 degrees and so on. And up on the y-axis, they plotted the sort of the temperatures of those little fluctuations. And it's in microkelvins squared. So when they plot it, they get these series of humps and bumps and little depressions and peaks and so on. Long story, so we won't go there just yet. But needless to say, it is the characteristics and strengths and patterns of those peaks and troughs that cosmologists are able to work out the relative amounts of dark matter, which is roughly 24%, normal atom matter, baryonic matter 4.6, and dark energy at roughly 71.4. And that helps form what we call the cosmological model, or the lambda CDM model of the universe. The lambda stands for dark energy. It's an energy, mysterious energy that drives the universe out, that's driving a lot of the expansion we see today. And CDM stands for cold dark matter. Cold meaning it's traveling at low velocities. It's not charging around at high speeds. It's low speed dark matter. So that's the abbreviation they call it. And they get all these sort of values, if you will, from these measurements, studying and measuring these little speckles of microwave in the background sky. So from there, they put it in their computers, and they put all these figures in, and to test it, they were able to predict how the sky on really, really large scales, like as in hundreds of megaparsecs, how the average distribution of galaxies should be. And as you can see, these little circles here, that's all because of another interesting tale called baryonic acoustic oscillations, which, yep, we'll talk about them, but not today. But needless to say, that they predicted you'd get these sort of statistical patterns in the sky. And yeah, the deep sky surveys, in particular the Sloan Digital Sky Survey, shows the average statistical separation between galaxies is this magic figure, 1.5 megaparsec, which means this is pretty successful. So using the measurements of the cosmic microwave background, how the universe appeared in its early days, along with all the values they got from there, they put it into their computer models, and then they asked the computer, well, how does that match up? What does that predict? The current rate of expansion of the universe. And their figure, 67.4 kilometres per second per megaparsec. And you might think, whoa, wasn't the last one 74? That's quite some, separate. Absolutely. That's a serious problem. It's called the Hubble tension. There's been a couple of studies. Let's focus on the Planck study, which I've talked about here. So 67.4 with a little bit of error, small error bars there. And there's another study involving the Microsoft background here. But these figures are over here. Look at here, these late time studies of the universe trying to work out the expansion through measuring these distances to these faraway galaxies using supernova type 1. This was the Reiss study. Here it is here. I've got here Adam Reiss and his colleagues. They got that 74. There's other studies, 73.3, 73.8, but with the error bars. But you see there's a huge gap. You can't even overlap the errors. That is called the Hubble tension. And yeah, it has serious implications. Do we need better and more, maybe some late time observational data? Are we, how good are we really with this cosmic distance ladder calibration? Is that accurate? Should we be doing other stuff? Should we be trying to look at other things to monitor? Is the Lambda cold dark matter model accurate? Do we need to tweak the values? Have we got those values wrong for dark energy and dark matter? Have our measurements of the cosmic microwave background, are they inaccurate? Are our sort of models and interpretation of those values need a bit of tweaking? Or is there a better late time observational method? In particular, as I mentioned, all those studies involving supernova type 1As were calibrated with Cepheid variables. Is there a better standard candle for calibrations of those supernovae type 1As? And the answer is, yeah, have a look at this. Here's another case study. So here was the Reiss and his friends in 2019. So Wendy Freedman and her colleagues released a paper in 2021, except she calibrated the supernova type 1A with the tip of the red giant branch, there's population of stars in a galaxy. So let's have a look at this. So she got the tip of the red giant branch she used, and she initially calculated that, as the other guys did, with a combination of objects of varying distance, as the other guys did, really to try and hammer home. So they looked at the Small Magellanic Cloud. That's another satellite galaxy. It's about 200,000 light years away from the Milky Way. And they looked at the detached eclipsing binaries there, and they matched them up with figures. They did a color magnitude diagram of the Small Magellanic Cloud, and they looked at the value for the tip of the red giant branch there, and they calibrated it. They then got some globular clusters within the Milky Way and the Large Magellanic Cloud. They then did some calibration with globular clusters. There's a luminosity function with globular clusters you can use, and also there's what they call RR Lyrae type of variable stars. We haven't gone into them. If we went over all the methods, we'd be here till midnight. So, but needless to say, they did further calibration. They then got stars. They found some Cepheid variables from the Large Magellanic Cloud, which is about 160,000 light years ago. We talked about that last time. They calibrated that with the tip of the red giant branch. They then went out to the nearby galaxy. Here's that galaxy again, NGC 4258. They used the lovely big water mega maser there, and they used that as calibration for the tip of the red giant branch of stars in that galaxy. They then were able to use that well and truly calibrated tip of the red giant branch in some of the more distant galaxies that they were also observing these 1A type supernova. And you might say, what was the results? Roll of the drums. Yeah, 69.8. That's a lot closer. And that arguably is relieving, it's certainly reducing the tension. It's relieving that Hubble tension. And here's a nice little diagram that's accounting for the error bars. Here's your cosmic microwave background measurements of the early time measurements, 67.4 with your error margins. Here's your Cepheid variables. This is one of the studies that showed 73.9 with some error margins. Look, you're struggling even to lap up the error margins. Look at this study using the tip of the red giant branch. Look at that, with the time you put your error bars in, there's some nice overlap going on in here. It's not a magic bullet, but there's a message there. And that message is our ability for precision local distance measurements to the sort of late time measurements to galaxies within our local universe needs to be better understood. They still, there's some errors sneaking in, unknown errors that are sneaking in. And I think we should be looking at that before we start throwing around claims about, maybe we haven't got our models of the cosmological model of the universe and dark matter and dark energy. They're not right. No, they're well and truly proven. You'd be struggling to challenge someone on those. Those have proved to be showing amazing predictions of how the universe has evolved over time. So people were reluctant to go messing around with those. And it looks like, indeed, before you start looking at other physics, do we understand the physics of the universe? We need to look at our ability to measure distances to these galaxies far away and to calibrate them. And a possible solution is the tip of the red giant branch. So let's go over some sticky messages now. One, what are you going to tell people? What are you going to think tonight when you close your eyes in bed? There are numerous methods used to measure distance to faraway astronomical objects. We've just reviewed a small number today. There's loads of different methods. And no one method is a perfect match. No one method does the whole lot. They've all got errors. And it's a combination of the methods is used as that cosmic distance ladder for calibration and trying to optimize the accuracy to the best way they can. And the third message is the Hubble tension reveals unknown errors with current methods in the local universe. So those are your three messages. So I thank you for your attention. I hope you've enjoyed Measuring Distances in Space, Part 2, the Cosmic Distance Ladder and the Hubble tension. And once again, I've put my email address down there if you want handouts for parts 1 and 2, or you just want the link to last month's talk because you're scrambling trying to find it on the website. Hey, that's all cool. Okay, Steve, so any questions there?
Yeah, thank you, Chris. We have got a couple of questions from Joseph. The first one he asks is, the term Cepheid variable is derived from a star that's not visible in the southern hemisphere. Any southern hemisphere Cepheid variables?
Good question, Joseph. I can't answer that question for you, but probably a quick Google will tell you that one. I'm a little bit surprised. Look, the honest answer, I don't know. But from our southern hemisphere, we always get nice views of the Milky Way because the plane of the Milky Way is sort of yay, and we're sitting up a little bit. And the southern hemisphere is actually looking down at the Milky Way, and that's why we get beautiful views, and we get far better views in the northern hemisphere. The northern hemisphere, astronomers and stargazers flock down here to get a view of our sky. So, look, I don't know. I couldn't quote where all the Cepheid variables are, so I can't answer your question. Quick Google would probably tell you that one. But yeah, it's interesting.
I did a quick Google for you, and
Yep.
yeah, there are quite a few. In fact, there are more in the southern hemisphere than in the northern hemisphere, so which
That.
is as you'd expect.
Yep.
So
As you.
Beta
Yep.
Doradus, Zeta Geminorum in Gemini, Artia Auriga in Auriga, Eta Aquila. So yeah, there's quite a few that are visible from the southern hemisphere.
Yay for the southern hemisphere! Go southern hemisphere!
Joseph had a second question that was about Cepheids, and he made this comment just as you were talking about the fact that they're not too common. He does say, but their brightness makes them easy to spot, right?
Yep. Correct. Yeah, the big plus is they're so easy to spot. Yeah, they can be up to 100,000 times brighter than our sun. They're blazing away. But because they are the end result of OB stars, main sequence stars, which are very rare. And it's called, Joseph, the initial mass function, how there's a natural tendency of nature to produce heaps and heaps more smaller stars, your K and M spectral class, and as you get bigger and bigger, they make less and less of them. And it's not just a pyramid, it's exponentially. And I've got a pie diagram, which I sometimes bring up, which shows it. And like sort of your red dwarfs make up about 75% of stars in the main sequence population. Your O and B stars make up less than 1%. It's actually a percentage of 1% for your O and B stars combined. So the amount of O and B stars compared with the others is tiny, which hence makes these red supergiant Cepheid variables. Yeah, they're pretty rare, but as you say, they are bright. You can pick them out, and that's why astronomers use them.
Thanks, Chris. And we got another question from a YouTube user with the name of Cicada, who says, so is all of the matter that we see in the cosmic microwave background about the same distance away, or are we sort of looking into a cloud of material?
When you're looking at the cosmic microwave background, you're looking at how the universe was when it was 380,000 years old. And of course, that matter has all just dispersed. We're in that. We're amongst all that lot, by the way. We're bathing in that, not looking back at it as such. We're bathing in amongst it. It's all around us. And all that matter is just separated out. Now, I'm trying to get my head around that question again, Steve. Could you repeat the question for me, please?
Yes. So, yeah, the user says, is all of the matter that we see in the CMB about the same distance away? I assume they mean from us. Or are we sort of looking into a cloud of material?
And that could have answered in terms of, yeah, we're looking at the variations of the matter. That's probably a way of looking at it. The variations about it. We're not looking at all the matter because we're not looking straight through it. Because remember, the universe prior to that was opaque. So we're just immersed amongst that. I'm unsure how to answer that question specifically to make sure I've answered it right. I'm unsure.
Thanks, Chris. I probably can't help you with interpreting anymore. Cicada, if you want to get in quickly with a clarification, we can do.
And Cicada, you're welcome to email me more specifically with at membership at Astronomy, and I'm happy. Some people do that later. A day or two later, someone will come up with a question and email me, and it gives me a bit of time to try or come back with another question to them, make sure that I'm answering the question right. So feel free to do that. But I'm a little bit perplexed by it, to be honest. Yeah.
Thanks, and there are no more questions. So thanks again. That was super interesting part 2. I was certainly riveted by it, and I'm sure our other viewers were too.
Yep, it's great. And next month we'll be in person. Yay! All things going well. And it's going to be on the James Webb Space Telescope. So something more exciting to talk about. That's all good. So good night, everyone. Thanks for tuning in. Cheers.